So hi everybody, I hope that you are all well. Today we are going to cover some interesting subject. Just a minute. Actually, we are going to cover two papers. One about multiple view geometry using the infinity norm, and one regarding the related idea, which is called projective least squares. And let's start. So you are all familiar already with this slide. This is the structure for motion problem. And we all know that we would like to solve the following problem. We have projection xij in the image of a scene point j in image j, and we would like both to find the cameras and the 3D points in the space. We'd like to make some sparse reconstruction with the cameras, the location of the cameras. So we discussed it a lot, and we define what is the reprojection error. Actually, the reprojection error is the distance between the measure and the projection of the point in the 3D space using the estimated parameter of the camera. This is the reprojection error, actually. Okay? And actually, in the last lecture, Amnon talked about bundle adjustment optimization, where this is the objective. And we understood that we need a good initialization to solve this problem. And actually, this is a refinement solver for the structure for motion problem. You don't solve it directly in general. And we studied some local optimization methods for solving this problem, including Newton and Levin-Marquette and Gauss-Newton. And you're all familiar with this, I guess. Okay. Today, after we discussed how to optimize this challenging objective in a way to optimize it, this nonlinear least square problem, we are going to look today at very special cases of this objective, which will enable us to make things easier in some cases. What do I mean by that? So this is the objective that you are all familiar with, and we denote the camera matrix by P. The left block is consisting of row A1, A2, A3, and the right vector is consisting of T1, T2, T3. This is a matrix, as you already know, 3 by 4. The point in the 3D space is X in homogeneous coordinate. And now let's make some algebraic derivations to this expression, okay? So just plug in the notation that I have in the left, okay? And making some arrangement of the numerator and the denominator, some simple algebraic manipulation. And then actually I get the same what I had before, okay? And if the camera metric is not known and the points are not known, actually I have the same objective. I have coupling between A and X. This is the unknowns. And we discussed how to solve it. However, let's say that somebody told me what are the matrices, what are the camera matrices. I mean that I know all these A's in this expression. And then it means that I have no more coupling between the unknowns, the A and X, because A is known, and I'm looking for the X's. Okay, so let's say that somebody told me the camera matrices, and I'm looking for the X's, the unknown, the 3D point. So what do I get in this way? Actually, if either the cameras are known or the points are known, I'm getting a least square problem, but different from what we had before, since it is quotient, every term is the quotient of affine function. Okay, this is an affine function of x divided by affine function of x, and this is another affine function of x divided by affine function of x. Is it clear? This
Also t is known?
Let's say that t can be known or unknown. It does not matter for the affine expression. Okay, let's say that t is known, or it doesn't matter for now. Okay, but it's a good question. You can assume that it's known or unknown. Okay.
We already have the method to solve it if we know the camera matrices, right?
Right.
And point.
Good point. Let's talk about it. Good point. Right. Great. So I'm happy that you are all with me. So let's continue and discuss what you just raised up. Okay, just before the discussion, if we denote the optimization variable by some parameter where we call it v, actually we can take each residual, like what we had before, and we saw that each residual can be written as some affine expression of v divided by the affine expression of v, another expression of v, again affine divided by the same expression here, like this. And in a minute you will see why this is a restriction, that the denominator should be positive. Okay.
We'll now discuss the methods of solving the general affine projective least squares problem.
Right. And you ask a question why you are going to do this, because we already have a method, right? But in a minute I'll answer to your question. So the idea of this objective is called affine projective least square, and there is a very nice way to solve it, and even to get a global minimum, and we're going to discuss it. Just want to give you some motivation and to answer to your question. So the form of the residual is like this, or like this. If you look at the squared residual, and let's see some example. So we are going to explore some examples such that the residual looks like this with this constraint, or the residual squared look like this with the same constraint. Okay. So first thing we can discuss is triangulation. Let's say I have in this case the full camera matrix A and T, and actually I'm looking for X. So I have quotient of affine function in X, and actually it's very reasonable to say that the denominator is positive, since the scene point should be in the front of the camera. As we already discussed, this is actually measure the distance from the camera of the scene point, right? So this should be positive. It's okay. It's a reasonable argument. Okay, this is triangulation. Now let's take another example. Resection problem, right? In this case, we would like to estimate the camera matrices where we know the 3D points in the world, and of course we know the projection, which are denoted here by small x, like this. Okay. Again, we have affine function of A and T. Okay. And would like to solve the camera resection problem. Another example. Okay, we have the camera orientations. Okay, we don't have the translation, we don't have the point in the 3D, and would like to solve for them. So here, for example, Shiran, you just asked before. Here, for example, I know A, which is the rotation, but I don't know T, I don't know X, and I would like to solve for both of them. Again, when xj is visible in the camera, this is the constraint that I have to take into account. Okay, so we have already 3 examples which are very useful, and as Rafael said before, we already have a way to solve it. So why are we going to invent another way? Okay, so this is the situation, and let's see why. So we are familiar with the algorithm for solving this problem, homogeneous least square, or DLT, how we call it. So why we are looking for another algorithm for solving these problems? Since the algebraic algorithms does not have a geometrical explanation, and here the objective is geometrically meaningful because we minimize the reprojection error. When you go to some algebraic scheme, sometimes we forget about the geometrical meaningful or meaning of the objective, and this is the way things are done. Okay, and here note, here we have geometrical meaningful objective. Moreover, this is also statistical meaningful under the assumption that we have the Gaussian noise, as you have saw in Amnon's lecture, in Ronen's lecture. Another issue is that in contrast to the DLT, here we do not need to normalize the image coordinate. And the reason is that actually we are in the geometric space and in the metric space such that we do not need to normalize the image coordinate like what we had to do in the algebraic solver. In the geometric solver, we do not need to do it. It's a delicate issue, but following the paper, it seems convincing. Okay, and moreover, as you see next, we are going to find global minimum to the problem. Okay, so the idea is,
can you remind about the normalization in the triangulation? What we did, we at the end divided by the fourth coordinate, right?
Yeah.
Or this is what you call normalization, right?
Normalization, I mean, not exactly normalization. I mean that you take the image coordinate that you have in the matrix, and if you remember, it was x and y, and x and y was in pixels, and then you had the homogeneous representation of x and y, and then for the homogeneous there was 1 in the matrix, and then the matrix got very how do you say, very high condition number due to this, and we normalized the points x, y, and 1 such that the scale of x1 was approximately near 1, and then we managed to solve the problem with our problem. Here you don't have to do it.
Okay, thank you.
This is called normalization. Okay. Okay, so there is a trick of the optimization. I'll give you some motivation, and then I'll try to convince you that it works. And the trick is the following. Actually, we're not going to solve the L2 norm problem. We are going to solve the L infinity problem, okay? And actually, instead of solving the least square optimization problem, we are going to solve something else, which is called min-max optimization problem, because what is RV infinity is exactly max over RIV over all the residual, and I'm going to minimize the maximal residual.
But L infinity doesn't really sensitive to outliers?
Great, doesn't sensitive to outliers, and I would say that also L2 doesn't sensitive to outliers. You're right.
No, I mean it does sensitive to outliers, right?
L infinity is not robust to outliers, and also L2 is not robust to outliers, right?
Not in the same manner. Like
I agree with you. I agree with you. Just to say that in this kind of problems, like what Amnon talked about last time, the bundle adjustment, and the kind of problem that I'm talking today, the idea is that before you construct your objective, you filter out outliers. You don't work with outliers. If you want to work with outliers, it is not the right scheme. Okay? This is the idea. You assume that you have noise. You don't have outliers. Okay? Okay? So this is a good point.
Yeah, what is under changing the norm from 2 to infinity?
What is it? Sorry?
What is why would we like to move from L2 to
okay, I know. I'll explain everything, and you will see why in two lines. Okay, okay, okay. So what we're going to do, we are going, instead of solving the least square optimization problem, we are going to minimize the maximal reprojection error instead of the sum of the square reprojection error. Why do you do this? As Michael asked, why? And the answer is the following: the L2 norm optimization problem is a non-convex problem, and it has multiple minima, and therefore you can stack in local minimum. The L infinity norm optimization problem is not a convex problem. However, due to some characteristics, it's possible to compute the global optimum, and this is the reason. Okay, this is the idea. And we'll understand the scheme exactly, and everything will be clear later on. Okay, so let's take a very, very simple example, triangulation example, when we make some one-dimensional cross-section. And here what we have a camera that we know the parameter of the camera and the location and everything. We have the image, and we have a measurement of the projection of some 3D point, which I don't know. And this is the projection of the 3D point somewhere in the space, in the 3D space, and this is the projection of the 2D image. What I know is that, just for, for illustration, I know that this projection comes from a place here, which can be parameterized by some 3D point U0 plus, sorry for that, plus some term, which I don't know, which I call T, times direction, which I know. Okay, just for illustration. So I can parameterize the location of the 3D point, which is the which will be projected to UI as some U0 plus some parameter, which I don't know, times direction, which I know. Okay. Now I'm going to show you that. So first of all, this line, as we know, by perspective projection, is going to be a line in the image. Now, if I'll take a ray from the camera, okay, to this line in 3D, and I'll look at the projection, okay, and I measure actually the reprojection error between the red line and between the red point and the black point, okay? And I measure this distance, what we call reprojection error, and I measure for some value of t, and then for another value of t, okay? I'm moving with the t, okay? I'm going to measure this distance, and again, okay? And again, till I'm reaching the exact solution. Then it can be shown, okay, that the distance between the red point along this line to the black point, like what is written here, can be written as, okay, the distance, the reprojection error squared can be written as exactly what we saw before, some affine transformation of t squared plus affine transformation of t squared divided by affine transformation of t squared. This is a very simple example. And how does it look like? Okay, let's look at the next slide. So if I take very, very specific example, and I'm taking very simple affine expression, another affine expression divided by t squared, another simple affine expression, this is the landscape of this simple function. As you see, it's not convex. Okay, it's clear that it's not. However, it has a single minimum, although it's not convex. But if I'll take sum of such function, a simple function, and I sum them, okay, then I'm going to get multiple minima. However, if I'll take the max over such function, I'm going to show you that any local minimizer is also a global minimizer. So this is the benefit that we are going to have. Instead of working with summation, we are going to work with the max, okay? So this is the most...
I understand that when you looking on specific residual, so it's non-convex, but you have one global minima and you can reach it. but when you reach it, you probably increase the error for other residuals. And then you make yourself alternate between residuals.
No. Let me convince you that when I have such functions, can be in many dimensions, not very simple dimension like this. And when I'm looking at the residual, then such a collection of functions, if every function behaves like this simple function, the maximal function is going to behave very similar. Let me proceed and you will be convinced, okay? This is the topic of the lecture, so let's move on and you will see. Okay, so in order to move on, we are going to understand what is quasi-convex function and what properties quasi-convex function share with convex function. Some nice property, not all, some nice properties. And then we are going to look at very special convex sets. One which you are familiar with this is called half space, and the other is called convex cone. All of this will enable us to understand how to construct an optimization problem that will lead us to global minimum, okay? So let's continue. I just very briefly remind you the benefit of convex functions. So as you remember, any convex function on a convex set, it turns out that any local minimum is also a global minimum, okay? I'm not going to give it the proof here. It's in the slide. You can take a look at later on, okay? Another very nice property of convex function, that if you take non-negative sum of convex functions, note that it's a convex function, then the resulting combination, it's also a convex function. So if I'll take f times alpha, and alpha is positive, f1 plus f2, every such combination, when I'm starting with convex function, I'll get a convex function. This is a very nice property of convex function where quasi-convex functions are not going to share, okay? But they are going to share something else which is very useful. Here it is. If I'll take the maximum of convex functions, okay, f1 and f2, pointwise, then if f1 and f2 are convex, then the maximum is also a convex function. Very easy to see it from the definition of convex function. So if this is f1 and this is f2, then this is the maximum. And the maximum, this one, is also a convex function, not necessarily differentiable. Actually, if you start with something differentiable, not necessarily get something differentiable. And actually, quasi-convex function share this nice property. In a minute, we'll determine what is quasi-convex function. If you start with quasi-convex function, the maximum operation, okay, will let you have another quasi-convex function. In a minute, we'll understand what is a quasi-convex function, okay? Another very nice issue of convex function, which is related to quasi-convex function, we are all familiar with the term graph, okay? When we look at a pair of point x and fx, but there is another issue which is called epigraph, and actually it's the points x and t, okay, the concatenation of x and t is such that x is in the domain of f and fx is smaller than t, and actually it looks like this. If this is the function, this is the epigraph of the function, which means that the region above the graph of the function, and there is some very nice interesting properties of convex function that link between convex sets and convex function, saying that a function is convex if and only if its epigraph is a convex set. Okay, this is now there is another issue with convex function. There's something which is called sub-level set of a function. You are familiar with level set, and what is sub-level set? Sub-level set of a function. It's all the point in the domain of f, such that the value of the point is smaller for alpha. So given alpha, I'm going to determine the sub-level set C alpha, and alpha is fixed, okay? Then I'm going to determine all the point in the domain of F such that the value at that point is smaller than alpha, okay? Sub-level set of convex functions are convex for any value of alpha, okay? This can be proved very easily by 2 lines. I'm not going to go over it. You will look later. However, the converse is not true. A function can have all its sub-level sets convex, but not mere a convex function. And actually, this is a quasi-convex function. A function such that all its sub-level sets are convex, okay? And this is the special functions, class of functions we are going to discuss today. So I'll give the formal definition. A function is called quasi-convex if its domain and all its sub-level sets, okay, are convex. Let's see an example. Here, for example, we do not have convex function, sure, okay. But if I'm asking myself, what are the values? What are the values in the domain of the function that the function value are smaller than alpha? So immediately see it's between A and B. And this is a convex set, of course, okay? What are the values of the function? What are the points in the domain of X such that the values are smaller than beta? And you immediately see that it's between -infinity to C, like this. So this is not a convex function, but all the sub-level sets of this function are sets such that the sets are convex. Okay, is this clear?
No, can you repeat the last sentence?
Yeah. So I'm trying to say the following. Any convex function with convex domain, of course, if I look at this expression, what is this expression? Given alpha, which is a value, okay, in the y direction, okay, the value which denote the value of the function, and I'm looking at all the axes in the domain of the function, such that I turn value smaller than alpha. For example, like here, let's look at alpha here, okay, and I look at this, the value of alpha. What axis in this domain get value smaller or equal than alpha? So immediately see that this is the values between A and B. Okay, do you see, Michael? It's okay?
Yes, I didn't understand why beta is also is convex.
Okay, let's see. Let's look at beta. What values? From here to -infinity, right?
Yes, but the function is not convex. You said are convex.
Good question. That's the good point. This is a quasi-convex function. And the definition of the quasi-convex function is a function such that it resides on convex domain and all its sub-level sets are convex function. As I said before, any convex function has convex sub-level sets, but the other direction is not true. You can have function like this, which we call quasi-convex function, okay, such that the sub-level set of the function are also convex. This is definition of quasi-convex function. Now it's clear?
No, again, I don't understand why you said first of all you said that if the function is convex, so the sublevels are convex. I understood. Now it's the other stuff. You say if the sublevels are convex, it's not necessary that the function is convex.
Right, exactly, because it's not in two directions. Okay.
Okay, but beta is not giving me a convex function. So it means that not all the sublevels are convex.
Why not? Beta give you interval between -infinity to C, right?
Yes, but in less than A in the domain, yeah, I start to get a not convex area.
No, I think you get convex area. Please take a careful look and you will convince yourself that everything is convex. You get just one interval, not two intervals. Just one interval.
Not the function should be convex, but the values in the domain of function should form a convex set. So you should look not at the function.
Okay.
Got it, Michael? It's okay?
So the interval needs to be convex.
The interval, I say the interval, yeah, good, yeah.
Okay.
Okay, the interval, like this, A and B, between A and B, between minus infinity and C, right. Okay, so I guess now we are, everything is clear. So if we look at one dimension, actually in one dimension we can characterize very nice quasi-convex function. It's either non-decreasing or non-increasing, or there is a point which we call C, such that from one side it's non-increasing, from the left side it's non-increasing, from the right side it's non-decreasing, like this exactly. And actually this C is a global minimum, okay, of the function C. This is in 1D. It's not our case, just to let you have some intuition. It's not our case. As we have quasi-convex function, we have quasi-concave function. What is it? Instead of looking on the value fx smaller than alpha, I'm looking at the value fx larger than alpha. Okay? And again, here I'm getting intervals between this and this, between this and this, okay, etc. Just to let's see some examples. This is a quasi-convex function. This is a quasi-convex function in 2D. However, is this a quasi-convex function?
No.
No. Why? Exactly.
You have two intervals.
We have two intervals, right? So this is not a quasi-convex function. It's not a unimodal. And actually, this is the lower part here. It's a quasi-convex function and a quasi-concave function, both. Okay. Another example for quasi-convex concave function. Sorry, if I'll take f on the positive orthant, okay, and the function is xy times x2 on this domain. It can be shown that the super level sets, okay, not what we had before, the sets such that x1 times x2 is greater or equal to alpha for given alpha, also convex set for alpha, okay? This is just an example.
Yeah, so you're saying that every function that has only one maxima or one minima are quasi-convex or quasi-concave.
No, not exactly. In a minute you will see why. Sorry, it's a bit delicate. In a minute you will see why. Okay, okay, just a very good question. Just let me, I'll show you in a minute. So there is something which is called quasi-linear function. What is it? It's quasi-concave and quasi-convex, both. Examples, the rounding function like here. And in this case, the level sets, not exactly, are convex function, like here. The level sets are going to be convex function, okay? Interval, 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 or points like this. Not very important to our discussion, but just to let you have all the situation. It can be shown that quasi-convex function is quasi-convex if and only if the domain is convex, and also the value of the function at the convex combination of x and y in the domain is smaller or equal than the maximal value between fx and fy, like this. Okay? So generally, when we had convex function, we took the line segment above the two values of the function, and we said, okay, this is a convex function here. It should be smaller or equal to the maximal value between the two endpoints. Okay, this is equivalent definition. Now, for a convex function, we know that any local minimum is a global minimum. What happens in the case of when the function is convex? Okay, so we see immediately that it's different from the convex function. Here, for example, the gradient is 0. But this is a local minimizer, not a global minimizer. He is the global minimizer. So in some sense, they do not share the same nice property. However, here it is. An important property of quasi-convex function is that any strict local minimum of quasi-convex function is also a global minimum. Okay, and this is the reason that we can use this nice property to get a global minimum. Okay, just to understand the difference between this and convex function, let's look at the simple example. I have quasi-convex function and I have another quasi-convex function. When I take the summation of this quasi-convex function, I do not get the green one. Is not a quasi-convex function. You see, you have two modalities. However, the max of this pink and blue function is going to be a quasi-convex function. Okay, so we have the important property that any strict local minimizer or a quasi-convex function is also a global minimum, and we have the important property that if I'll take non-negative weight maximum of quasi-convex function, I have another quasi-convex function. Okay, and this is going to help us a lot in the derivation of the optimization scheme. Okay, I hope it's clear. Okay, let's continue. So I'm recap what we said. We solved min-max optimization problem, which look like this: minimum over the maximal residual under constraints. We minimize the maximal reprojection error. Okay, under the assumption that the residual are quasi-convex. I didn't show it yet, but I'm saying that the maximum of the residual is also quasi-convex. And then we are going to obtain what we call a quasi-convex optimization problem. And I'm going to define it in a minute. Okay, and we get the nice property that any strict local minimizer is a global minimizer. We still need to show that RIV is a quasi-convex over convex domain. We didn't show it yet, okay? And we still need to understand, even we have this property, how we are going to solve it, okay? And this takes us back to the formulation of constraint optimization problem, and we are going to discuss it, okay? So we have this formulation of constraint optimization problem. We have objective, we have inequality, we have equality, and we have what we call the feasible set, which means all the x such that the inequalities and the equalities are satisfied. This is called the feasible set. Sometimes the feasible set, omega, has some content in it, okay? Because there is intersection between one inequality and another inequality, but sometimes it can happen that omega is empty. What's the case? In this case, we say that the problem is infeasible because the constraints cannot satisfy. They contradict each other, okay? So this is the formulation, the general formulation of the optimization problem. And what happens in the convex optimization problem? In the convex optimization problem, we have convex objective, convex function for the inequality, and affine function for the equalities. If you want to ask yourself why just affine function for the equality, any idea why just affine function for the equalities? And not something else, not another convex function? Why I can say that this is a convex function, general convex function? Why is it? Any idea? So actually, we would like to have convex domain. And we know that the sub-level set of a convex function is a convex, so this is okay. But we don't know that the level set of a convex function is convex. We know that when we have here an affine function, we are going to get a convex set. Okay. So actually, in convex optimization problem, the inequality can be any convex function, but the equality are only affine. Okay.
Can you repeat that?
Yeah. Actually, this is the situation. The objective is convex, okay? And we would like to have intersections in the feasible set. We would like to have intersection of convex sets, right? So if the function is convex, I know that the sub-level set in this case, for example, of 0 is going to be a convex function and convex set, sorry. We know that this is a convex set, okay, due to what we just discussed before. Any convex function that I'll take, f(ix) smaller or equal to 0, going to give me a convex set.
Correct. Even if it was quasi-convex, it is true.
Great. נכון. Okay. But for the equality, the only function that's going to give me a convex set is just the affine function. For example, think about something like quadratic constraint. It won't give you the equality, it won't give you an affine function. And a convex set. It give you something which is not a convex set. The only function that will give you a convex set is the affine set. This is the reason. Okay, so this is convex optimization problem. And what is quasi-convex optimization problem? Here, the same constraints, convex and affine. But here, I permit myself to have a quasi-convex function. And I want to solve it, okay? This is the situation that we have. We are going to have an objective which is quasi-convex and feasible set which is which consists of intersection of convex sets. Okay, this is what I'm going to solve. Okay, so I'm sure you remember what is convex set. Convex set is a set such that if you take any two elements and you take the convex combination of them, like here, you get another point in the set. For example, a line segment. Here, the left one is convex set, and the other two are not convex set. We discussed also affine set. In the affine set, I don't have a restriction on theta. Theta can be any number in R. And this combination, the affine combination, if I have a affine set, any two elements with this affine combination are going to be in the set. So if the example before was a line segment, now the example is the entire line. And we, in the lecture that I gave before Amnon, we have shown actually that any affine set is a convex set. The other direction is not true. And any affine set can be written as a system of linear equations, such that the affine set can be always written as the null space of A plus some shift, where shift the x0 is in the set C. And we say that the dimension of C is actually the dimension of the null space, which it's n minus m. Okay? Why I'm saying all this? Because I'm going to speak about something that you are supposed to be very familiar with it, and we're going to use it in our optimization scheme, so we need it. And I'm going to say what is a hyperplane. Hyperplane is an affine set of dimension n minus 1 in Rn. And actually, it's equivalent to say that I have a set of the form, the dot product, the inner product between A and X equal B. All the X's that obey it are in this set. And this is the hyperplane. I'm sure you're familiar with this. So this is just illustration in 2D. This is A transpose X. A is the normal vector to the hyperplane. Okay? X reside on the hyperplane. And actually what this equation says, it says the following. If I'm looking at the inner product, and I'm making some derivation, I see immediately that the set of points with constant inner product to the normal vector are going to reside on this line. Okay, I'm sure that you're familiar with it. Okay, so it's not I don't have to repeat it over and over again. Okay, so this is the idea. You take all the points such that the inner product with the normal vector is a constant. That's what is written here. Okay, this is the hyperplane. You can have it in R2, in R3, etc. I'm sure you all know it. So this is actually an affine set. What is the? This is another illustration. Let's move on. It's not something new. What is the half space? The half space actually is the following. You take the hyperplane and you divide it into two half spaces. The half spaces are convex but not affine, and this is the mathematical definition that A transpose X smaller than or equal to B. again, this is the situation. We have some hyperplane. This is the normal vector to the hyperplane. On this side, A transpose X is smaller or equal to B. On the other side, A transpose X is larger or equal to B. So I'm summarizing. This is a hyperplane, which is affine set. This is one half space. This is another half space. Any half space is convex, but not affine, okay? And we are going to use it in a minute, okay? So let's move on. So we already know things about hyperplanes and half spaces. Now we are going to discuss cones because we need it for our optimization problem. So what is a cone, okay? A general cone, I didn't say convex, is such that a set such that if I have an element in C and theta is non-negative, then also theta x should be in the set C, like this, for example. Okay. Here, for example, I have the 0 and I have the rays, and this is called the cone. This is another cone, not convex, but a cone. This, for example, a convex cone. Okay. Okay, so let's determine what is a convex cone. Okay, so it can be shown that a set K is convex cone, which means convex and cone if and only if any two elements in the set obey the following. If I'll take theta 1 and theta 2, which are non-negative, then the combination of them, the conic combination of them, will be in the set. Okay. The proof is in the slide. I'm not going to go over it. Let's move on. But this is the idea of convex cone, and this is very important. We are going to use it in a minute. Okay, just I want to recap the all ideas of the combinations, that everybody will be on the same page. So I have the affine combination. Okay, in the affine combination, the sum of the coefficients should be equal to 1, but I don't have any restrictions. And affine set are closed under affine combination. I have the convex combinations, okay? Okay, if I want to take combination of elements in the group, here I have the sum of the coefficient should be 1, but the coefficient should be non-negative. Convex sets are closed under convex combination. In the cone combination, the only restriction is that the coefficients are non-negative. In this case, convex cones close under cone combination. Okay, so this is just to recap. Now let's go back to our optimization problem. And to go to our optimization problem, I want to show you something which is very important to understand, something which is called a very special cone, and I want to explain what is this special cone. Okay, so in order to do it, I would like to remind you that if I have a norm in Rn, okay, and you remember that norm is also convex, right? So if this is convex, why for given R this is a convex set? Any idea?
It's the sublevel set of convex function.
Go right. So if this is a convex function, and we know that it's a convex function, we discussed it a lot. Then for a given R, this is a sublevel set of a convex function, and therefore this is a convex set. And this is example you're familiar with it. This is for L1 norm. This is a convex set. This is the unit ball. This is also a convex set. And this is a convex set for x infinity, etc., etc. Now this is the issue. You have to be with me now. Okay. What is a norm cone? We just discussed the norm, and we say that this is a convex set when R is fixed. But now I want to show you something which is a generalization, so what we had before, and the norm cone is the following. I'm looking at a set which is at Rn plus 1, and I'm looking at all points such that the norm of x is smaller than the t. T is a scalar value, okay? This is called norm cone, And actually, this norm cone is a convex cone. And it can be shown by definition very easily. But perceptually, be with me, and this is the idea, okay? This is example of a convex cone, of a norm cone in R3. And here what you see is the envelope, okay, the boundary of the convex cone. And each point satisfy here such that if I'll take x and t, this is x1, this is x2, and this is t, each point here satisfies the following inequality. The norm of x is smaller or equal than t. It's very intuitive, because what does it mean? It means that if t is 0, this is very narrow one, is just one point. If I'm going up with t, I am enlarging the disks and I'll allow the set to be wider and wider, right? So this is going to infinity. And actually, this is a convex cone. And this is a convex cone in R3. And it has a special name. It's called the second order cone, SOC, in R3. And you have it also in a general case, in Rn plus 1. In Rn plus 1, the norm of x should be smaller than t, and the point are x and t. Here we can visualize it, okay? Is this clear? What is the kind of this convex set or convex cone? Should I repeat? It's hard to me to understand. Should I repeat, or it's clear?
It's okay.
No, it's okay.
It's okay.
Okay.
Just, can you explain the last equation that you?
Here?
No, in the black. On the.
Here? Okay. Yeah. I'll explain. So this is for R3. Okay. Now I want to write it for Rn plus 1. So this is just the definition of the norm cone. Okay, x and t such that the norm of x is smaller than t. This is scalar, okay? And you can write it also in a kind of a quadratic form. I can say this x and t such that x transpose x smaller than t squared, but I have to take into account that t should be greater than 0.
Why t squared?
Otherwise, you will not get a convex cone. You will get some cone and some cone in the other direction. Okay? You have to keep the t is larger than 0. Okay? And if you want to write it in a more sophisticated way, you can write it like this as a quadratic multiplication. And actually, since it's a quadratic multiplication, this is the reason that it's called second order cone, like quadratic and second. This is the relation, second order cone. SOC. If you heard about SOCP or SOC, this is the SOC, second order cone. Okay, it can be in any dimension. This is a convex cone, and we are going to use it in a minute. Just I want to understand what's the time. Just sorry. Would you like to take 10 minutes break, or you are how are you? Let's would like to be here in 10:20. It's okay with you?
Yes.
Let's take 10 minutes break, okay? Because we have something other. Okay, 10 minutes break and we continue. Okay. So I just remind you that you would like to solve the following min-max optimization problem: mean over the maximal residual with the following constraints. This is the formulation of the residual. This is the kind of residual we have. So we already know that this constraint is convex constraint. Why do we know that?
Because it's inequality.
Because it's an open half space, as we saw before, right? Just saw that this is an open half space, and this is an open half space. Okay, this is an affine expression of V, and we know that a half space is a convex set, okay? And this is actually a half space, okay? So this already, you know, so the constraint is convex, okay? And here we have a element-wise max operation. And we know that if the function are quasi-convex, okay, then the maximal, the function which is the maximal over these functions is going to be also quasi-convex. So if we'll show that RIV is quasi-convex, then the maximum is going to be also quasi-convex, okay? So that's what we are going to show. Okay, so I claim that RIV is a quasi-convex function. And how I'm going to show that this is a quasi-convex function, how we show that function is quasi-convex? Any idea? So we just say that a function is quasi-convex by definition if its sub-level sets are convex sets, right? So I would like to take this function, and under this constraint, I would like to show that for a given gamma, C gamma, the sub-level set, okay, is a convex set. Is this clear?
Yes, yes.
Okay. So I'm going to show that RIV for a given gamma, okay, this relation, this sub-level set is a convex set, okay? So what is RIV? This is RIV, what is written up there. And I'll take into consideration that gamma is greater than 0 and the denominator is greater than 0. Everything I square, okay? And I'm getting this. And I'm getting, by multiplying this by this, I'm getting this expression, right? And I'm going back to here, and I'm getting that the norm of this vector smaller than gamma times this affine combination, right? Recall that gamma is fixed. And I claim that this is a convex set. I mean that gamma is fixed, A and B's and C are known. I just have the optimization variable V, and I claim that this set is convex, okay? It's not easy immediately to understand why this set is convex for a fixed gamma, but anybody else has an idea? And if it's true, then RIV is going to be a quasi-convex function, okay? But I'm asking why this is a convex set. Any idea? So let's try to make it slowly, okay? So we know that norm is a convex function, right? And this is a norm of some affine mapping, okay? This is a convex function, right? And we know that affine function is convex and concave, and this is fixed. So we know that this is a convex function, and this is a convex function, right? So all of this is a convex function. Therefore, if this is a convex function, the resulting set is going to be a convex set. Is this clear now?
Yes.
Yes. Okay. This is one way to look at this expression. A more complicated way to look at this expression is related to the convex con that we discussed before. Okay, first of all, we have this idea that this is a convex function because it's a norm and I have affine expression inside, and this is a convex function because it's just an affine term and gamma is fixed. Okay, it's not a variable. Then all of this is a convex function, therefore the resulting set is a convex function. Convex set, sorry. But from another perspective, recall that in before two lectures, we discussed affine image of a convex set C. And we said that if I have a convex set C, the inverse affine image of a convex set is also a convex set. So if I have an affine mapping F, and am I looking at a set which is convex, am I looking at the elements such that their mapping are in C, then the resulting set is going to be convex also. Okay? And this is the situation what we have here. Why? Because this is also a convex set. Why this is a convex set? Since it's applied to the second order cone. I mean that this is an inverse affine mapping of the second order cone. Just a minute, sorry. Okay, is this clear? So you can understand it from here, which is very easy. And you can understand it from the more complicated explanation. And the idea that we need the more complicated explanation is that this special way of second order cone allows us to solve this problem by using standard convex optimization problems. Okay, this is the idea that I want you to understand also the complicated explanation. Should I repeat the complicated explanation again? Or is clear? Let me do it again. We know that if I have a convex set and I'm taking the convex set and I do affine mapping to the convex set, I'll get a convex set. That we know, we discussed it. But the inverse is also true. So if I have some convex set C, and am I looking at the element, okay, such that their mapping, their affine mapping is in C, this is called the inverse affine image of the convex set C, then the resulting set is also going to be convex. So what I'm doing now, I'm looking at the second order cone, okay? And I'm looking at some affine mapping, and I'm saying that I'm looking at all the point V such that this occurs. This occurs means that they reside, the affine mapping of V reside in some second order cone. And I'm claiming that the resulting set is a convex set due to this property. I hope it's clear now, okay? So for a fixed gamma, we know that this is a convex set, okay? For a fixed gamma. If gamma is not fixed, it's not true, okay? Because then gamma multiply V and this is not true anymore, okay? Any questions or should I go on? Okay, so this we would like to solve. This is the residual. And actually, now we can say that we have a quasi-convex optimization problem. Why is it? Because the residual are quasi-convex, and therefore the maximal, the residual also quasi-convex. This constraint is a convex constraint. So we have a quasi-convex optimization problem, okay? But still we need to explain how to find the global optimum. We don't know yet how to do it, okay? So I'm going now to write this problem in some equivalent form till we'll get some way, convenient way to solve it, okay? So I'm starting from here, and I'm writing the following equivalent problem. Why is it is equivalent? Let me explain to you. Instead of this, I'm moving it to the constraint, and I say the following. Minimize gamma such that the residual will be smaller than gamma, and keeping this constraint, okay? Now, before I had just this optimization variable V, now I have V and gamma. Gamma is a scalar, okay? And it turns out, just think about it, that if I minimize gamma, and gamma is indeed larger or equal than every residual, then gamma is going to take the same value as the largest residual, which means that this problem is totally equivalent to this problem. Okay, this kind of formulation is called the epigraph formulation. So I'll take the objective, I'll put it in the constraint, and I put here linear objective, very simple linear objective, just gamma. Okay? Just want to know that you are with me and I can, is it clear? Or just it's okay with you?
Yes.
Okay.
Yes.
Yes.
I'm happy. Okay. Okay. So let's move on. This is one equivalent form. Now let's see another equivalent form. So this is the original problem. This is the residual. This is the epigraph formulation we just discussed a slide before. Now I'm going from here to here. Minimum gamma, optimization over gamma and V. Just wrote here RIV, which is written here. Okay. And actually we know that this is exactly this. Okay. This is exactly this. And gamma greater than 0. Actually, I'm omitting this since if gamma is greater than 0, it immediately says that this should be in the same sign. Otherwise, it's infeasible. So now I'm neglecting this constraint, replacing it with this constraint, and I have a new problem. Minimum over gamma, optimization over gamma and V. Recall V is a vector, gamma is a scalar, such that this is the constraint for gamma and for the many constraints that I have, and gamma should be greater than 0. So this is the formulation that we are going to use. It's still quasi-convex formulation because it's still this for gamma which is not fixed, this is not a convex constraint because gamma multiply V. So I'm still have to think how to solve it, okay? And we are going to understand it in the following way. So this is a problem that we are going to solve, okay? This is the last formulation of the problem. We are going to solve it, okay? So we can say the following issue. For a fixed gamma, we know already that this constraint is second order constraint. This is a convex constraint for a fixed gamma, okay? Let's continue. The intersection of this constraint for a fixed gamma is also convex because intersection of convex set is a convex set. Let's continue. Now we are going to solve the optimization problem by a series of convex problem, actually convex feasibility problem over many values of gamma. And before we are going to do it, I would like to give you some intuition. Let's look at the following movie. We have a triangulation problem. Okay, we have the cameras, and we have here 3 images, okay? And this is the direction of the cameras. And for every camera, we have actually its own cone of constraints, okay? It looks like this. This is one cone, this is another cone, this is another cone, and actually the 3D point must lie in the intersection of the cone. If the cones are too narrow, like what we have here, there is no intersection. With this mean, gamma is too small. If the cone, let me do it again. I hope I can do it. Okay, I'm not sure. Just want to run the movie again. Okay.
Maybe it goes like that.
Here it is. Okay. 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 So this is large gamma. I have intersection, etc., etc. But this error can be too high. So if I reduce the cones, the gamma, I reduce the error. But I can reduce the error, but still I would like to have some intersection. This is the idea. So how are we going to do it? So for a given gamma, I would like to determine, is there any intersection between the cones or no? This is called a feasibility problem. Okay? Is there intersection or no? Okay? Now how I'm going to do it? So now gamma is fixed. Now I'm going to introduce another slack variable. I call the slack variable C. Gamma is fixed, and I'm asking myself, find me the minimal S such that all the constraints are satisfied plus this slack variable. This slack variable is going to let me know whether there is intersection or there is no intersection. Okay? And this is just what I told you before. This kind of optimization problem is called second order cone programming. And this is the reason I was so insisting that you understand also the complicated explanation. This is a standard optimization problem that you can plug and use it. You don't have to invent something which is not there. And I would like just to convince you why this explains me if I have intersection or I do not have an intersection. Let me explain it to you. Anyway, this is already for a fixed gamma. This is a convex optimization problem because all of these constraints are convex, and this is an objective which is linear, so it's also convex. So you can just take any optimization toolbox and use it immediately by this formulation. The formulation is called second order cone programming, or SOCP. But why this let me have what I want, okay? So given gamma, let's look on the option of S, okay? So for each selection of gamma, we solve this feasibility problem, okay? Just say it's called second order cone programming. Let me let you know. So if S is greater than 0, recall that I'm minimizing S. If S is greater than 0, what does it mean? That my constraints are not satisfied for this gamma, okay? Why? Because if they were satisfied, I would able to lower S and not get positive S. If I'm getting positive S, it means that I cannot satisfy this constraint, okay? That's what I mean. It means that gamma is too small. Do you understand it? If
Yes.
S is negative, it means that the current gamma is larger. It's too wide, it's larger than the min max, okay? It means that the constraint can be satisfied. So I have some condition for a first gamma to know whether the constraints, the cons that I showed before, are intersecting or not. This is the idea. Now, it's possible to search for the minimum value for the what we call the required gamma by solving a sequence of convex problem, okay? And here it is, the pipeline. So this is called bisection procedure. We minimize the maximal reprojection error, and we solve the problem in the following way. First of all, we looking for gamma L and gamma U. That's the lower and upper bound for the optimal error. We know how to do it. We just do it by the feasibility problem before. And such that the min max reside between gamma L and gamma mu. And we know how to do it. We just discussed it before. And we have some accuracy that we want to get. So we solve the convex feasibility problem and check whether there is a solution that satisfies the following new gamma. If RIV is smaller than the average of the two bounds, okay? If there is a solution, okay, then I update the upper bound. If there is no solution, I am updating the lower bound with this. In this manner, I'm bisectioning the interval between gamma L and gamma mu such that at the end, when gamma mu are close to gamma L up to epsilon, I know that I'm in the interval of the optimal value. And this is the way I'm attacking this problem, okay? Is this clear?
Yes.
Okay. Yeah. Actually, this is the way you attack any quasi-convex problem. You know, just you have to somehow to frame it as a convex feasibility problem, and this is the way you do it. What about computational complexity? So if the accuracy is epsilon, And each iteration, I divide the interval by 2. After k iteration, this is the size of the interval. 2 to the minus k times the difference. And if I wanted to have it smaller than epsilon, k should be log of the interval divided by the epsilon. Of course, as the interval is large, I would pay more, and if epsilon is too small, I would pay more, but this is the idea. Okay. So I would like to recap and to say a few things about the L2 norm. And I would like also to say that I think that tomorrow, the day after tomorrow, we are going to distribute an exercise that will recap all this idea, and you will ask to calculate triangulation or something else with respect to this problem using the projective least square idea, write an optimization problem. The idea is that you are not going to write exactly how to optimize. You are going to use ready toolboxes of optimization. We inspected the toolboxes in Python, and we'll let you have exactly what to do with the right libraries. This is going to be a programming exercise that you will. This is going to be the next homework for you. Okay, so tomorrow, the day after tomorrow, we'll have it ready. Working on it. So I just want to recap. So if the camera we started for an example. This is an example that we talked about. Let's say that they have the camera orientations, and I would like to solve for the points of and the translations. So this is exactly a problem that we discussed before, just one kind. And here it is. I want to recap the idea. So we say that special cases such as triangulation, camera resection, if homography estimation can be formulated as often projective least square problem. And this is actually L2 norm of residual. We didn't solve the L2 norm. We solved a surrogate problem. We minimized the L infinity norm of the residual. And we showed how to recast it as a quasi-convex problem. The problem has a geometric meaningful criterion, which is very nice. This is in contrary to algebraic methods. And the quasi-convex problem can be solved by a sequence of convex optimization problems. Okay. Now, I would like to make some disclaimer to say the following. The problem with the L infinity direction is that somehow we lost the statistical meaning formulation that we had before, and this is the reason that we still would like very much somehow to solve the least square solution, the L2, because it's statistical optimal, and L infinity is not statistical optimal. It has the geometric interpretation, but still does not have some familiar statistical meaning. Okay, so in the case of the L2 norm, under the assumption of independent Gaussian norms, the L2 norm give you the maximum likelihood estimate. This is the reason that I would like to solve it. So yeah, just for a few minutes, I want to just to make a few words about this. So eventually, if it's possible, I would like to solve this, okay? The L2 norm. But we know that sum of quasi-convex function is not necessarily quasi-convex function, right? Therefore, the L2 norm, as we said before, have multiple local minima, okay? However, let's assume that somehow we can get local optimum for the L2 norm, okay? So we have, and the value of the optimum is epsilon squared. Fv is epsilon squared. So actually, it means that the global optimum, which can be just smaller than this, must lie in this region. Why it must lie in this region? What is this region? This region is all the points, all the v's, such that the squared residual is smaller than epsilon squared. Why this is true? Because each residual must be smaller than the sum of all the residual. So somehow the global minimum must reside here. Why this is so nice? Because we know that these functions are quasi-convex. And since they are quasi-convex, the sets, the sub-level set that we have from here are also convex. So therefore, the intersection is also convex. So it means that the global minimum resides in a convex set, okay? And the idea of one of the paper that we discussed is the following. They say the following. They have a way to look at this very small set and say, and look for sufficient condition such that F is convex on this set, which means that just on this set, I'm looking for a condition that F is convex. F, it's the sum of the squared residual. And if it's true, then I'm going to get a global minimizer. And the idea is that they take F and they differentiate it and calculate the Hessian and analyze the Hessian and let us have very complicated condition for having the global minimizer. I would like to say that just looked at the citation of the paper and I was not very sure that they gained a lot of citation. I'm not sure it's very popular or not, but just want to let you this issue. The other paper, which discussed the infinity more, is more familiar and more cited. Just want to let you know. In the homework, you will not touch the L2 norm. We will touch the L infinity norm. We'll solve SOP optimization problems, second order cone optimization problem. And I'm done unless you have, we are also good in time. So if you would like to ask more or something else.
I understood.